In the last two videos, we talked about where time is actually spent and the difference between CPU-bound and IO-bound work. Both of those lessons hinge on one skill: profiling, knowing how to capture a trace, read it, find the bottleneck, and act on it. This is a skill that separates developers who fix performance problems in hours from developers who spend weeks guessing. And honestly, it is not hard. The tools are free. The techniques are straightforward. But most developers never learn them because profiling feels intimidating. Today we are going to demystify it completely. Let us start with the tool you already have, the Android Studio CPU Profiler. To use it, run your app on a device or emulator, open the Profiler tab in Android Studio, select your app's process, and click on the CPU section. You will see a timeline. When you are ready to investigate, click Record, perform the user action you want to analyze, then click Stop. Android Studio will show you a trace. This trace contains every method that ran during your recording, organized by thread. You can see the main thread, background threads, coroutine threads, everything. The default view is the call chart, which shows method calls as horizontal bars stacked by call depth, laid out over time. This is your flame chart. Let me teach you exactly how to read it. The flame chart has two axes. The horizontal axis is time. The wider a bar is, the longer that method took to execute. The vertical axis is the call stack depth. The topmost bar is the entry point, usually something like perform traversals for UI work or your coroutines invoke for background work. Below it are the methods it called, and below those are the methods they called, and so on. Your goal is to find wide bars at the bottom of the stack. Those represent methods that take a long time themselves, not because of what they call, but because of their own logic. If a wide bar at the top has many thin bars beneath it, the top method is slow because it calls many things, and you need to dig into which Kali is the problem. Color coding helps too. Android Studio colors system methods differently from your app's methods. Focus on your code first, the bars with your package name. That is where you can make changes. Besides the flame chart, Android Studio offers two other views that are incredibly useful. The top-down view shows you the call tree starting from the entry point. It is great for understanding the flow. This method called that method, which called this other method, and that is where the time went. You can see the total time and self-time for each method. Total time includes all Kalis. Self-time is just that method's own code. If a method has high total time but low self-time, the bottleneck is in something it calls. The bottom-up view inverts this. It starts from the leaf methods, the ones that actually did the work, and shows you who called them. This is perfect when you find a hot method and want to know why it is being called so many times. Maybe your deserialization method is slow, and bottom-up shows you it is being called from 5 different places. That is how you find the real root cause. CPU profiling tells you where time goes. Memory profiling tells you where allocations go. In the Android Studio Memory Profiler, you can capture a heap dump, a snapshot of every object in memory, and see how much memory each class is using. You can also record allocations in real time. Why does this matter for performance? Garbage collection. Every time Art's garbage collector runs, it pauses your app briefly. If you're allocating objects rapidly, say in a tight loop or during a scroll, GC pauses can cause visible jank. The memory profiler shows you exactly which classes are being allocated most frequently and where. The most common culprit, creating objects inside onBind viewholder or during compose recomposition. Autoboxing is another sneaky one. Using int where the system needs integer creates an allocation every time. The network profiler in Android Studio shows you every HTTP request your app makes, along with timing details. You can see when the request was sent, when the first byte arrived, and when the response was fully received. You can inspect headers, the request body, and the response body. This is invaluable for diagnosing IO-bound performance issues. Common findings: duplicate requests, where the same endpoint is called multiple times for the same data. Oversized responses where the server returns far more data than the app needs. Sequential requests that could be parallelized. Requests made on every screen visit that should be cached. The network profiler shows you the actual traffic, not what you think the traffic is. And the gap between those two is often surprising. When you need to go deeper than the Android Studio profiler, especially for UI junk, Perfetto is your tool. Perfetto captures system-level traces that show everything: your app's threads, the system's rendering pipeline, CPU scheduling, even power state. To capture a Perfetto trace, you can use Android Studio's built-in Perfetto integration or the command line. The resulting trace opens in the Perfetto UI at ui.perfetto.dev. In the trace, look for your app's main thread. Each frame should complete within about 16 milliseconds. If a frame takes longer, you will see a gap, a dropped frame. Click on the frame to see what happened. Was it a slow layout pass, a long recomposition, a main thread I/O call? Perfetto gives you the timeline for every thread and every system service so you can see exactly what caused the delay. Let me talk about a newer tool that is often misunderstood: baseline profiles. Remember how we discussed Art's JIT compiler? When your app first launches, RT interprets bytecode and gradually JIT compiles hot methods. This warm-up period makes your app slower on first launch. Baseline profiles let you specify which methods RT should pre-compile ahead of time. You capture a profile by running your app's critical user flows, startup, main screen, common navigation paths, using macro benchmark. This generates a profile file that lists the hot methods. When the user installs your app, Art precompiles those methods. Immediately, the result: faster startup, smoother first interactions, better first impressions. Google reports 15 to 30% improvement in startup time with baseline profiles. This is one of the highest impact, lowest effort optimizations available. Android offers two benchmarking libraries, and they serve different purposes. Macro benchmark measures full user experiences. App startup time, scroll performance, screen transitions. It launches your real app, performs real user interactions using UI Automator, and measures real metrics like time to first frame and frame durations. This is what you use for overall performance validation. Microbenchmark measures the performance of specific code paths in isolation. How fast does this function sort a list? How fast does this serializer encode an object? It runs in a tightly controlled loop, eliminating noise from other processes. Use microbenchmark when you are comparing two implementations of the same algorithm and need precise numbers. Use microbenchmark when you want to know if your app actually feels fast to users. Both have their place, but macro benchmark is usually more actionable because it measures what users experience. Let me walk you through a real profiling session. Say your product manager reports that the home screen scroll feels janky. Step 1. Reproduce the issue. Open the app, navigate to the home screen, scroll up and down. Confirm you can see the jank. Step 2. Capture a trace. Open the profiler, record during the scroll. Step 3. Look at the main thread in the flame chart. Find frames that exceed 16 milliseconds. Step 4. Examine the long frame. You see a white bar for on-bind view holder. Inside it, a white bar for image decode. Bingo! You are decoding images synchronously during scroll. Step 5. Fix it. Use coil or blide to decode images asynchronously. Step 6. Capture another trace. Confirm the long frames are gone. This took maybe 30 minutes. Without profiling, you might have spent days trying random optimizations. One specific profiling technique that catches a lot of developers off guard: finding allocation hotspots. In the memory profiler, record allocations during a specific action, like scrolling a recycler view. Then sort by allocation count. You are looking for classes that are allocated thousands of times during a short window. Common culprits: temporary string objects from string concatenation, auto-boxed primitives from using Java collections with Kotlin primitive types, iterator objects from for each loops, Lambda captures that create a new object per invocation. Rect and paint objects created inside draw methods. Each individual allocation is cheap, but thousands of them trigger garbage collection poses that cause visible stutter. The fix is usually simple: reuse objects, use string builder, avoid autoboxing in hot paths. Here is what I want you to take away from this video. Profiling is not an advanced skill. It is a fundamental skill that every Android developer should practice regularly. The tools are built into Android Studio. They are free, they are powerful, and they tell you the truth. Unlike your intuitions, the workflow is always the same: measure, identify, fix, measure again. Never skip the first or last step, and never optimize something you have not measured. If you adopt this one habit, profiling before optimizing, you will be more effective at performance work than 90% of developers. In our last performance video, we are going to bust some common optimization myths and talk about what actually works.